How's it going, everybody? Today I'm going to walk you through and build a parallel processing framework that I'm going to use in conjunction with MPI4py. So essentially the framework is going to be written in Python. It's going to be kind of a wrapper that abstracts the orchestration of the library for distributed processing away from the user so that the user just has to pass simple user-defined functions, and they don't necessarily have to worry about and mess with actually writing the parallel processing code. They can just leverage the framework, pass their own internal functions, and the framework handles the processing for them. So essentially what I'm going to be leveraging is the MPI4py library. And essentially what that is, it's a library written in Python, and it's using the message passing interface, which is a standardized and portable message passing system designed to function on a wide variety of parallel computers. So essentially, MPI is a paradigm in parallel processing specifically for distributed systems that have distributed compute or distributed memory and need to be able to communicate with each other in order to perform some sort of computation or processing in a distributed manner, right? So like I said, so it's going to be mostly used for like HPCs, so supercomputers, high performance computing, or any sorts of like in the cloud, you'll have multi-node clusters, right? So anytime you have some sort of distributed compute and you want to process across it. So an outline essentially of what the framework's going to kind of handle is we're going to have our master method, and then we're going to also have our worker method. But you're going to pass to that, your master function or your essentially your chunking functions and your initializations, your chunking functions, your worker functions, your results functions, and your final functions. So essentially to break that down a little bit more, what's going to happen on the master method is we're going to break the work down into chunks. So that's where we're going to be running our user-defined chunking function. It's also where we're going to perform any sort of initialization. So it's going to happen in our initialization function. So if you want to load any sort of information that you don't want to be duplicated on all workers, that's going to happen there. So that'll be like certain inputs, obviously the chunking information, the creation or initialization of any output files or directories. Also, the master method is going to control the orchestration and dissemination of the work. When using output formats that don't allow for parallel writes, it'll handle the results and the writing of the results. And it also what we'll be using to perform any of our final functionality. So yeah, essentially that's kind of the breakdown of the master method. Chunking function, what that's going to kind of handle is breaking down the work into chunks or smaller pieces that can be distributed. For us, we'll return a number of chunks and a chunk generator. So the work function, that's what's actually going to be what performs the provided algorithm or code on the individual chunk and returns / writes the results. So for us, we'll allow us to frame it so that the worker reads in required data and doesn't rely on the master to send it. You can kind of go two different paradigms, and the framework will allow for both, where either the master reads in all the data and disseminates the data to the workers. But for most cases, if you can allow for parallel reads, where the worker reads in its required data itself and performs some computation on it and then returns the results, that'll speed things up by not bottlenecking things. So allowing for that flexibility. And then a results function is, again, function provided that tells us what to do with the results. So we'll be run by the master node on the result in return, which is returned from the workers. So if we need to write an output to an output format that doesn't support parallel writes, it'll be able to be done there. Also a place where we can do some error and exception handling, and then also tracking of worker runtimes and things like that, right? And then the final function, which will be provided by the user as well, is any kind of wrap-up functionality that needs to be performed that you don't want. It doesn't necessarily need to be done by every individual worker, but needs to be done as an aggregate at the whole, and we can run this on a singular node, normally the master node at the end of the processing. So essentially, again, to kind of explain the concept of how we're going to handle like the parameter passing to the various functions. So obviously the worker functions or the user-defined functions, that being the worker chunking, initialization results, and things like that, depending on the use case, are not all going to have the same parameters and arguments required. So we're going to need a way to handle that. So the idea for this is to essentially require the user to initialize at the beginning of the process and send to the process as a dictionary or keyword arguments all of the internal parameters that will be needed by the internal functions. So we're essentially going to create a Python dictionary of these parameters, pass it to the processing class that we're going to create here in a second. And we'll just need to write a wrapper function. We'll create a decorator that essentially pulls from that dictionary all of the arguments and keyword arguments that pertain to each individual function. So generally speaking in Python, if we would pass a dictionary of a bunch of different key value pairs to a function, if some of those key value pairs aren't actually used by that function, it'll throw an error. So essentially what we're going to do is create a function that just pulls out the key value pairs that are needed and then not use the rest of them. So a little bit of an overview of kind of what the breakdown is going to be. So let's go ahead and dive right in. All right, so we're going to go ahead and import a couple libraries. So essentially inspect, this is going to be for that parameter passing function that we need to write. TQDM is essentially just a progress bar, so it prints out a progress bar while our work's being operated on, so we can kind of track things. And then wraps is also going to be used. So I'm actually just going to copy and paste the function that we're going to use as our decorator. So essentially it's going to be user defined. That's what I decided to call it. So essentially you pass a function to this, and then any of the arguments and keyword arguments that are then passed to that function, what it does is it takes a look at them and uses the inspect library built into Python. It looks at the signature of that function, and it takes a look at the parameters. So it also takes a look at the number of arguments we pass to it and fills in those where the original arguments would be expected. But then also it looks at the rest of the keyword arguments that we passed to the function, and it only grabs the ones that are in the function signature keyword arguments, right? So we essentially passed it a dictionary of key value pairs, and it just extracts the relevant key value pairs to this particular function. So not necessarily super important, the details of that, and there's probably different ways you could go about doing it, but this is kind of just what I've cooked up. But essentially how it would work then is you would just have the decorator user defined, and then you define my worker, and then let's say you need to pass a chunk as an argument, but then I also want to have arg1, arg2, and then at the end of it return something, we'll just say chunk. Essentially that arg1 and arg2, what we're going to do for that is when we, at the end of this, when we create our process, which will be parallel process, we'll create a class, we'll pass my chunk, my worker, and then my result, and then we'll actually pass extended quargs, right? So we'll pass any kind of quargs, and what that might look like for this, we would then just pass arg1 equals 1, arg2 equals 2, and these keyword arguments that are the end of this class will then be passed to our function, internal functions. We could also initialize things for initialize different arguments that need to be passed, or different variables that need to be passed to different functions that don't pertain to your worker. So let's say arg3 equals 3. And what this essentially this decorator will do is it'll just ignore this arg3 and it'll just pass the 2 arguments that are needed for your particular function. But okay, so just kind of explain a bit of that use case and how that's actually used. Let's go ahead and dive in. So I actually wanted to start with creating a serial process version of this. So just to kind of explain what's happening without diving into the MPI4py stuff right away, just to get you the logic of what's happening and how this works under the hood. Also, it's I found it's useful to have a serial processing version of the class. That way I can use it for like debugging and things like that without having to actually run things on a distributed system. A lot of times when you're working with HPCs, you're going to have to wait in like the queue and stuff like that, and wait for resources. So it's kind of nice if you can just grab a single node resource and run things in a serial manner to make sure things are working properly. Make sure your code's working before you actually send things up in like a Slurm job submit and send things to the distributed system. So we're going to go ahead and do that first. So essentially what you're going to need to do is going to be required by the user, like we talked about. They're going to have to pass their chunking function, their working function, and then a result function. So how do they want to chunk up the work? When it is chunked up, what do they want to do with it? And then when you get the results, how do you want to handle the results? Things they can provide are initialization functions and a final function, but those things are not necessarily required. So initialization is something that if you want to make output files or output directories, things like that, but you don't necessarily need to do that. It's not always required in every job. And then same with the final functionality. Like sometimes you don't have any wrap-up functionality that needs to be completed, so you don't necessarily need to provide that function. So we're just gonna go ahead and create these internal parameters here. Self.rfunc equals result func, and then self.initfunc. Okay, so we've essentially initialized these within the class. So now I have internal parameters that we can work with and initialize to our actual instance. So next thing we're going to have to do is we're going to go ahead and define our master method. So this is going to take self and then all of the kwargs. So like I showed you before, any of those keyword arguments, all of the internal parameters that we pass to the class will then be passed to this master method. So the first thing that's going to need to happen here is kwargs.update self.ifunc. And we're also going to pass the kwargs to that. And that is if self.ifunc is not none, else print no initialization required. Okay, so essentially what this is doing is since we passed that dictionary of keyword arguments to the class, and which is getting passed to our initialization function, what we're going to do is update that dictionary, updates kwargs with output of initfunc, which means needs to return a dictionary, right? So essentially, like I said, this kwargs is essentially just a dictionary, and we're going to want to update that dictionary with any additional parameters like paths to output files, paths to output directories, things like that, if needed. And so in order to update that, we also need to return another dictionary so we can update it with another dictionary. Okay, so the next thing we're going to do is we're going to go ahead and get our total chunks and our chunk generator, which is our cfunc. And then again, passing those parameters. All of these internal functions, so user, are going to be decorated by the user defined. So you're going to have define my worker. And then so forth. So go ahead and create that just to kind of showcase as we walk through this. Go ahead and do chunks and result as well. So chunks is going to have to return a dictionary, and it's going to take any keyword arguments that you need that are initialized within your class. My worker, so once we get to that, we'll kind of walk through that. Okay, so for the next part though, we're going to go ahead and iterate through the chunks. So range total chunks, result equals chunks. Oops, sorry. Result and chunk equals self.cfunc, and then again passing that kwargs to it. So essentially what this is telling us is that, oh sorry, this should be worker. So that's our worker method. So we're going to be applying our worker method, which needs to return result and chunk, and we're again passing our kwargs to it. And then the next step is we're going to go ahead and run our result func. So self.rfunc result, and then we're going to pass it keyword arguments, and then we're going to actually create a dictionary. So we're going to pass chunk as our chunk. Or kwargs. So essentially what this is doing is saying we're going to pass to our result func our result plus a dictionary which contains our chunk and any of the other keyword arguments. The reason why we add the chunk here, and essentially what this is doing is this dictionary or this dictionary, which creates a dictionary of both. And essentially why we're doing that is because we don't know, especially once we get to the MPI, we don't know exactly what chunk we're working with. We don't get that until we start to perform the operation. So we want to pass to our result func which exact chunk we're working on. So that's essentially what's happening there. So what this means is, this should be chunks. Oh, and sorry, I missed a spot here. So this should actually be next chunks none. Okay, so essentially what this is happening here is we're on our master method, we're going to go ahead and initialize. If we have an initialization function, update our kwargs with any return parameters from that, create our total number of chunks and our chunk generator on our master method. And then what we're going to do is we're going to iterate through all those chunks, and we're going to send to our worker the next chunk from the generator along with any keyword arguments. And then from that, we're going to get a result, which we're going to send to our result func with keyword parameters that include which chunk it was operating on, plus all the other keyword arguments that were sent to the master method. So pretty simple. It's kind of like a for loop, really. It's pretty just a little more kind of convoluted for loop, but the idea is it's abstracting away from the user any of the actual orchestration of, sending the chunks, iterating through them, performing some kind of operation and returning the results and handling the results. So we're going to go ahead and define our worker method. So this is going to need to take in our chunk, right? So self.worker takes a chunk plus keyword arguments here. So it's going to take in our chunk, plus we're going to take in our kwargs. And how this works is if chunk is not none, then results equals self.wfunc on your chunk and keyword arguments. And then we're going to go ahead and return results and our chunk. So right here, the worker method is expected to return your results and your chunk, right, which we did. And your work func expects a chunk. So we're going to go ahead and put chunk, and then any other arguments that you need to pass to it, which are also initialized in the beginning of creating your class, which come from the kwargs, right? And then the last thing we need to do is define our final method. So self and then kwargs. And this one's pretty straightforward. So self.finalfunc on, again, passing those keyword arguments. If self.finalfunc is not none, else none, right? So pretty straightforward, pretty simple. Oop, this should be if. There we go. If self.finalfunc is not none, else none. So pretty straightforward. It's kind of just like a little bit more complicated for loop. Essentially passing in your user-defined functions, your chunk work result, and then optional init and final function. Initializing, adding in those new arguments from the initializing function, creating your chunks with your chunking function, and then essentially just iterating through all the chunks, passing them to the worker, getting the results, and handling the results. So pretty straightforward. The next thing we're going to do, though, is we're going to actually go into the parallel process, which is going to look very similar, but it's actually going to be using the MPI4py library. So instead of serial process, though, we're going to go ahead and call this the parallel process. So pretty straightforward. So for this, though, what we're going to go ahead and do is up at the top and import MPI4py. And we're also going to initialize a couple of variables here. So MPI world equals MPI.com world. And essentially what this is just this, this is just our communications. Okay, sorry, we're actually going to go from MPI4py import MPI. There we go. So this is just essentially our communications across the nodes. And then essentially what we're going to do is call MPI world.barrier. And this is just synchronization. So essentially what's happening is when MPI4py, when you have your cluster of distributed workers, essentially what happens is you tell it to run this script. And what it does is it runs this script on every single worker at the same time, so in parallel. And what this does is this initializes the communications across all the workers. So each worker gets its individual rank. And all this barrier is doing is it's synchronizing things. It's making sure that every node runs this script up until this point and stops and waits until all of the rest of them have been initialized and have communications. So anytime you see this barrier, it's just a synchronization point where you're making sure all of the scripts run up until this point before continuing. So we want to make sure all of them are initialized in the communications. Okay, so now we're going to go ahead and go back to our parallel process. Oh, I did forget something though. Let's go back up to serial process here. So we actually need to define the call function, right? So like what's actually happening when you call it. So we've defined all the methods and stuff, but we don't actually see what's happening. So what we're going to want to do when we actually call this, again, is pretty straightforward. The first thing we're going to go ahead and do is print serial processing begins, just to make sure we know that it's running here. And then all we're going to do is call it self.master method on the self.quargs. And then we're just going to go ahead and return self.final method again on the self.keyword arguments. So pretty straightforward, just calling that master method again because the master actually controls the workers as well in the serial processing framework. And then for the final step, we're going to go ahead and return that final method and the results with it. Okay, so again, to get back to the parallel processing now, we're going to go ahead and start with defining our master method for this. So we're actually going to go ahead and pass self, and then we're also going to need to pass the MPI world so that it has access to the communications across all the nodes. And then again, just the keyword arguments. So what I like to do is parallel processing begins. So we're calling this on the master node because we just want it to be ran once. We don't want it to be run on every single node. And then what's kind of nice, the thing I like to do is also print out the number of workers that have been initialized. So we're just going to go ahead and call MPI world.size. The .size method returns the number of workers within our world, right? Okay, and then the next thing we're going to do is we're going to go ahead and get our MPI status. So this gives us the status of all of the workers and the situation of everything we have working together in the distributed system. And then again, we're going to go pretty simple. We're just going to do quargs.update. So updating that keyword argument dictionary with our ifunc. Again, passing the keyword arguments to that. If self.ifunc is not none, else print no initialization required. All right, and the next thing, again, we're just going to go ahead and get our total chunks, and our chunks equals self.cfunc, passing in our keyword arguments. All right, so then the first thing we're going to do, this one's the part where it starts to get a little bit different, is give out starting functions or starting chunks to each of our workers. And so how we're going to do that is for worker in range 1 MPI world, MPI world dot send next of chunks or none if there are none left, and then destination equals worker. So essentially what this is doing is it's sending out an initial chunk of work to each worker, except for not to the master, because essentially what we're going to consider the master node is the one with rank 1, and then the rest of them, so 1 to the rest of size, is all going to be all of our worker nodes. So essentially for worker, which would be 1 to however many workers we have, we're going to send the next chunk of work out to each individual worker. So each worker gets a number, which is called their rank, between 0 and however many you have. 0 being the master node, and then 1 to the rest being all the workers. So essentially they got their rank, and you can call that rank using destination here. Okay, so now that we've sent out the initial chunk of work, the next thing we're going to do is we're going to listen for results and handle them, then send more work. So essentially how we're going to do that is for in TQDM range total chunks. Essentially what we're going to do is result chunk. So it looks very similar to what we have up above, MPI.world.receive. Source equals MPI.any source. Tag equals MPI.any tag. Status equals MPI status. So essentially what this is doing is it's listening for results from any of the MPI workers, so any source with any tag based off of our status, right? So listening for results from any of the workers. Once it gets those, then it's going to go ahead and perform the self.rfunc, so as user-defined result func. And we're going to pass it the result, and then we're also going to pass it again that dictionary of which the specific chunk we're working on, or all of the keyword arguments, so all of the downstream parameters that we need, which were sent by the user and defined by the user. Had a couple extra commas in there. Okay. And then once we get that, then we're going to go ahead and send a new chunk if there are any remaining. And so what we do is we just go ahead and do mpi.world.send next chunks or none, and then destination equals MPI status dot get source. So essentially what this is doing is, listening for results from a worker. Once it gets a result, performs the result function on it, whether that's writing the results out or what have you, sending to that result func, which specific chunk it's working on, and then getting the source that came from and sending a new chunk of work back to that worker to keep things going and to make sure we're utilizing all of the resources efficiently. So again, what this kind of tells us is our result func up here needs to have result, and then again, any other arguments that you might need, but you have already defined. Because that is being passed as an argument and the rest are being passed as keyword arguments. Okay, so the next thing we need to do is define our worker method. So self and then MPI world. And then again, any keyword arguments. And this one is essentially chunk equals MPI world dot receive source equals 0. So this is when the workers are going to be listening for work to be sent to them from the master node, which is going to be source equals 0, so rank 0. So while chunk is not none, results equals self.wfunc, and then on the chunk, and then again, keyword arguments, and then mpi.world.send. Then we're going to send back to it with the results and the chunk. And then we're going to send that back to destination equals 0. So send that back to the master node. And that's pretty much it. So now that we have defined our worker method or master method, just to reiterate exactly what's happening. Essentially, the master method is getting the MPI world once that's already been established. Everything, all the workers have comms. coming in, we're performing the initialization function if it's been provided. We're creating the chunks of work, getting the number of chunks we need to work on. We're starting out, giving out our starting chunks, sending those out to the workers, and then we're going to sit and listen for the results to come back. As results come back, we perform the results function on it, and then we send a new set of work out to that worker and keep things going. What the workers are going to be doing and what the worker nodes are going to be doing is just basically sitting and listening for data or chunks to be sent to them from the master node. And then while those chunks are not none and they are actually something we want to compute on, we're going to go ahead and perform that worker function on it and then send the results along with the specific chunk we worked on back to the master node. So the last thing we need to do here is define the call method. So what happens when we actually call an instance of this class. So this is when the compute actually starts. So we're going to go ahead and go self.master, and again we need to send MPI world to it along with any self.quargs, and then we want to run this if and only if MPI world.rank equals 0. Else we want to run the self.worker method, and then that also takes MPI and then also our quargs. And then after that, we want to go ahead, and this is where the synchronization comes in again. You want to make sure that all of that work is run and the script continues and waits for all of that to be processed before stopping. And then once everything has been computed on and we have all of our results calculated, then we can go ahead and run our final function or our final method if MPI world.rank equals 0 again, else none. So all the workers won't be doing this, just the master. And then we want to go ahead and call barrier again just to make sure. And then we're going to go ahead and return our results. So there we have it. There's kind of our parallel processing framework. We also have a serial processing framework. I've kind of laid the foundations for how you might use this in a use case and how to set up your different functions. And essentially the workers or the user is just going to have to create their various functions, and then they can go ahead and run their script. So just kind of show you what that might look like. They would go ahead and make a process object, and we'll just call it the parallel process. Make it one of those. They'd go ahead and pass my chunks, my worker, and then my result. And then if you go back and look, so you're going to need to have, this isn't exactly right, but let's say we need to have arg1, 2, 3, and 5, right? What they would essentially have to do is come down here and just say arg1 equals 1, arg2 equals 2, arg3 equals 3, arg5 equals 5. And now that they've initialized that class, then they would just go ahead and call the process, and it'll go ahead and perform their compute and handle everything for them, right? So they just have to make sure they pass their user-defined functions and all of their keyword arguments or all of their arguments for those functions as keywords arguments to the parallel process class, and then it'll handle all the orchestration for them. So I think in some follow-on videos, maybe I'll walk through some more specific examples and actually how to use this and actually run some things, and how to show how to run things with MPI4py and how to run things parallel and serial manner as well. But for now, I hope you enjoyed, and I'll see you in the next one.